Hello, welcome back to our CSCI 430 operating system, and we will continue to our lecture. Okay, and just like I review what we covered in the previous lecture. So we did a talk about the too much milk, this situation. Myself, we compared different solutions, so including the kind of like in the solution three, it looks better because we adding like adding a note and then checking given a while, like checking condition. Okay, so if we checking the others threads or like other rumors, okay, say okay, if they are not without a note, then of course um we can execute the if condition. If there's a note exceed, then we just do nothing, like just keep running the while loop and just wait until the flag that means a note, okay, change to false. Okay, so here's the decision. But here's the things, because it's possible when we discuss about like multi-threading. Okay, so it's possible that okay, we may be execute for some, like let's say if there's not the critical section, if you remember critical section, so it's a atomic action, so we only like execute. But for the no milk, this one maybe is not that perfect. Also, it's like complex, right? So why that's why we maybe need to waiting for it. So it will call the busy waiting. Okay, so we want to comes out a better way. Okay, given a better performance. Okay, and supporting. That's why we come like a fourth solution. Okay, so we have the acquire. Okay, so this one is like we will wait until the lock is free. Okay, and then just grab it. So it's more like the concept if we are waiting for the event, right? If you remember. So we just like put in waiting. Okay, once um the event occur, and then also of course we have the release. Okay, we can unlock it and wake up like anyone like waiting. So it's a better way, but we need to be careful. There should be atomic like operation. So if there are two threads, so we talk about waiting for the lock. So only one succeeds to grab the lock. Okay, so all this we say that occur, and then also the release, they should be atomic action. So it comes out, so it will be better and safe, like instead of using the while loop. Okay, so it will be better. So we can grab it and then we can check, okay, if no milk, then we can buy milk. Okay, so this is a critical section and then the atomic action. Okay, so this is how we're going to execute. This we're going to cover. And then next, we talk about the neutral execution. What's the hardware support? How can those hardware approach like to supporting like the neutral executions? Okay, so in the beginning, then we will ask a question like where are we going with that synchronization, right? First, in the beginning, so let's say we do have a high level API, then we can share those like programs including the logs, okay, semaphore, okay, monitors. We will talk about for the log you will already saw example, right? And also later you see what's the semaphore, okay. And the monitor we're going to discuss, of course, we have the send and receive the message, okay. And then how about the hardware, including the log will be load and store, okay, or the disable int, okay, or sometimes we can like compare and then they swap it or the exchange. So this more hardware level. So when we go into the implement, like the various high level synchronization, okay, primitive, then we are going to use the atomic like operations. Okay, so make sure so they are like we have to compete. Okay, so all those operations, okay, it was together. It cannot be interrupted. Okay, stop. Okay, and everything is like pretty painful. So if only atomic primitive they are low and stored. Both of you like you already know. So we're going load and stop should be like atomic operation. So we need to provide a primitively useful at a user level. Okay, so that's how we're gonna do. Then how we actually like implement the logs. We already cover it. So this one. So because the logs prevent someone from doing something. So logs I have as like before enter a critical session and before the accessing sharing data, so we can lock it. So we need to unlock it, okay, when leaving after accessing the shared data. So the example right here, the last solution we're using. So here's the lock, okay. So we need to lock it and then unlock it. And we are locked, then we of course will wait. Okay, so we wait on it. Here is very important. So like all this, we need to implement the synchronization. So involving the waiting. Okay, so maybe we are well, waiting the queue, or like we need to put in the sleep stage. Okay, if we need to like waiting for a long time. Okay, so we depends on the design. Okay, or the how much time need to like wait. Okay, sometimes we never know. So once like we do have mechanism decided, and then we can like say, okay, excitation time, and we will put it to sleep. Okay, stage. Okay, and of course, right here, then we will for the hardware, we need to support one thing is they for the interrupt disabling. So for example, for the uniprocessor system is not common nowadays, but just need to know when we like disabling the interrupts, so we can't like guarantee them to execution. Okay, um what's the disadvantage if we going to like do this? Okay, so the efficiency of execution, okay, could be like noticeably degrade. Okay, here are things. And also this approach will not work in multiprocessor architecture. So you need to know interrupt disabling currently working in uniprocessor. So just but when later when we discuss in multiprocessor, or like most like nowadays all these system is not useful at all. Okay, so you need to know, and just know the keyword for the this hardware support is it disable the interrupt is impossible. We need the interrupt. Okay. Also, there's one is called the atomic, like to call the read modified write instruction. So what's this? So these are more like getting a problem. We talk about the microwave. So we cannot like we can't give a lock implementation to user. Okay, then we may make acceleration. Okay, or actually you should know why we couldn't give the information of the log to user. If the user can change the log, okay, that means if we change the sequence, then it may affect it, right? So it kind of similar to the while. Okay, if I can change my while condition, okay, or do nothing, I change to do something, so it will destroy. Okay, design. So that's why. So also it doesn't work on the multiprocessor or multi-core. Okay, here's things. So because we're thinking, okay, so we have multi-thread on a single processor, and then we grab access if we have like multi-processor grabbing same time. Okay, so we need to think about, do we have any atomic instruction sequence? Okay, so this like instruction, they read the value from memory and then write a new value atomically. Okay, that means like read and write. Okay, a new value. The hardware so is responsible for implementing like this like correction. Okay, so on both like unit processor. Okay, unit processor is easy, but more important like we need to consider is like in the multiprocessor. Okay, multi-cores. Okay, because we require to help from the like cache. Okay, like coherence like protocol. You need to know. Okay, unlike the disabling the interrupt, okay, because the this interrupt, then we can without any um like jumping out, okay, going to event, right? So we can have a complete operation. So this one we can use like both a unit processor and my multi-processor. So it's like better we need it. So make sure like all the processor, and then make sure they enter the read, okay, and then write, okay. So it's the atomic, okay, operation. And also we can use that by normal user, okay, at a low level mechanism. Okay, so it will be better, right? So we just like cannot giving the some really like less in the log implementation to the user. And then the next the memory. Okay, so the memory, so for the read write, so excludes like other access to the same location. So we need to think about the design, because the CPU design have like propose a special machine instruction. So it carry out two actions atomically. So one is the read and test and set like this, or for example, like this. Okay. So during the execution of instruction, so we access to a memory location, so it's blocked for any other instruction. So it's a must write. Okay, so here's the idea. And also, what's the compare instruction? So we talk about, so this one, or sometimes we call it like compare exchange instruction. So we always try to like mix a compare. Okay, when they mix a compare the memory value and test value. Okay, if the value and then a test value, they're the same. So if we like doing, then we will like swap it. Okay. So it will also carry out automatically. So just like be careful. All the action we right here discuss and make sure we are not like only execute one or two instruction and then jump to another one. So it causes issue. So everything should be atomic like operation. Okay. Be careful. And right here, some you will see some sample code, or later you will see in more practice. So let's say we will try to compare what's the old value, okay, pointing to the word. Okay, if they match with the test value, then we'll assign, okay, and then we turn it, okay, the old value. So here's the called the compare and swap, okay. You will see the source code and also actually get implement. So you can see we using pointer. Okay, if you learn C purpose, so we are pointing, so it's actual pointing to the word. Okay, so we are not by reference. Okay, okay. And then here's a more like detail. Let's say we have the like program to execution, and then we have numbers. Let's say assume we have the number of process. Okay, and then we have an integer. Okay, bot. Okay, right here, and then we have a void function, return nothing, and then we have a while true. Okay, we keep like executing. So what we're going to compare, okay, we're going to compare swap, and then what's the bound, okay, 0 and 1. So if you remember the passing, so the word right here, compare, okay, first the word we're going to assign, and then what's the test value, and then what's the new value, okay. So we try to like assign the original word passing, okay, so old value, make sure the old value is then matched with the test value, okay, then we can assign, okay. So right here, the test value right here and one. So we just make sure, okay. So with the return value, because the return value, we return the old one. Okay, the old one, that means that the one we're going to pass in, the bot one. Okay. So when you pass it, so we make sure, okay, is it the return value is it equals to one? Okay. So if while yes, okay, we do nothing, and then if we can pass it, then of course we assign bot is equal to 0, and then the rest will be like anything. Okay, you see right here, you see the functions, and then more likely we care about the design of the structure. Okay, how can we make sure entire like this session? Okay, for the rest we don't really like care. So you see, but you see that we have the main function, and then we set the bot to equal 0, and then we have the bar begins. Okay, begin right here. Like let's say we have the P1, P2, okay, and until Pn. So once we're going to execute. So it depends on how many processes we're going to create. So we can have like Pn process, and then we can compare. So this one we just make sure like every time when we access it, and we have getting same value. Okay, return. Just like preventing here, like always like carry out, right? So just we need to make sure like compare it with the test value, and then if they can match, then we will swap it. So here's the most important part. So here's the word, like actually pretty easy. The old value compared with the test value. Okay, yes, then we assign, and that's it. Okay. And then what's the exchange? Exchange instruction. So it's another machine instruction. So it provides like on both like 30 or 64-bit Intel chips. Okay, so it's like working same. So right here, exchange register, we're passing with the register memory. So we setting a time. So it's a really common. Okay, so we always like creating third variables. Okay, temporary variables. Okay, we will storage the original memory one, and then we put the register value to the memory. Okay, and then we move the temporary to the register. Okay, so if you did vote, okay, the like some swap function, exchange function, okay, for changing the variables. So you know like at least we need to create extra variables and then to keep it and then swap it, right? So these are pretty straightforward. Okay, design of it for exchange. And then when we put it together, if we need to do exchange, then we can execute it. Okay, we have like two keys. Okay, when we exchange it and make sure the key I is not equals to 0, and then we get into the critical section. So this one is the hardware support return and the military execution. So for right here, we do all these things like we want to let the like applicable to any number of processes, okay, on the either single processor or multiple processors, let's share the main memory. Actually, for nowadays, like our design, mainly like all our hardware devices, they are multiple cores, right? So we have the multiple processor. So also we're going to share the main memory. So we need to think how can we implement like more simple and easy to verify. Okay, so that's how can we check. Also can be like used to support multiple like critical session too. Okay, so every time we have multiple session, how can each critical session can be defined by its own variable. So we need to think about this. So it can help using the mutual exclusion. Okay, and but so far, if we want to do this, we bring the disadvantage of the BC waiting. Okay, so when we decide too much milk, okay, this situation. So if we apply the solution three, okay, so also it occurs at BC waiting, right? So when it's employed, so first this while a process they are like waiting for access to a critical session, so it continues to consume like process time. So we need to think about that. Um, Starvation, okay, so like starving, like it can happen, right? So if possible, when process leave a critical section and more than one process is waiting, okay. More serious situation gonna happen is a deadlock. Okay, it's gonna happen. So we do need to think about that, right? So if you remember in our previous chapters, we too talk about what's the starvation. Okay, what's the deadlock? So you need to remember definition. Okay, and right here back to here the example. So we say right here occur right here and also release right here. So like in between we have the critical section. Okay, we make sure they are like we try to implement okay those like with a log, okay, like this. So we need to wait until the log is free, okay, or unlock it. So just a recall of it. Okay. And next we talk about the semaphore. Okay. So this one is how can we turn to software mechanism used to provide and manage concurrency. Okay. We're going to talk about that. Actually, right here we talk about some like common concurrency mechanism. What's the semaphore right here? So we need to know there's an integer value used for signaling. Okay, among processes. Okay, only 3 operations may be performed on semaphore. Okay, and all of like which they are atomic. So we start with the initialize and then decrements and increment, and that's it. And when we have a decrement operation, then we will blocking of process and then increment. So we will unblock it. Okay. So also know it's like counting semaphore, general semaphore. We have different names. Okay. Also we have the binary. Okay. So this one only taking values 0 and 1. Okay. We have mutex. Okay. Pretty similar to binary. The difference between like that is that the process they lock in the mutex, so we set it to 0, so must to be the one that we unlock it, so set the value to 1, so kind of like this. Okay, and we have the condition variables. All these are data type, so we use that to block process or thread until a particular condition is true. Okay, also we have the monitor. So here's a monitor we're going to cover to later. The programming language I construct the and capture variables. Okay, so we can access the procedures, initialization code within an abstract data type like this. So the monitor variables, okay, may only be accessed by the access procedure, and only one process like may be actively accessed the monitor at any one time. So we just remember only one time. And access procedures are critical session, okay, and the monitor have a queue of processes that are waiting to access it, so we need to know. And then the event fragments, okay, so it's a memory word like used as a synchronization mechanism. So the application code so may associate with different events and each like bit in a thread. Okay, so when a thread can wait for like either a single event or a combination of event, okay, by checking one or the multiple bit in corresponding thread. Okay, so the thread is block until all the required bits. So they're set. So like this, okay. And also just like until the last of the bit is set. Okay, right here. So just need to know we have the event. But also we have the mailbox message, okay, right here. So just like two processes, they exchange information. And we have the spin logs. So it's also the mutual expressions mechanism, which just telling us like that when the process execute in an infinite loop, so waiting for the value of a log variable to indicate the availability, and that's it. So it's the called the spin log, okay, spinning, okay. And for the semaphore right here, so it's a kind of a fundamental principle. So including like two or more processes. Okay, so process can cooperate by means of like simple signals. So step one, how can we like asking initialize okay to a non-negative integer, right? And then we have the decrement and the increment. So if you remember, so we have weight and signal. Okay, so weight is a decrement, okay, and then signal is the increment. So later you will see the functions like we have the same weight and same signal. So that what you see. Well, here just showing you what's the primitive way. If we have the structure, right? So I'm using the C purpose, the Q. So we have the count. Okay, Q type, we have the Q. So for weight, okay, we pass the symbol A S right here. So if for weight, because decrement we're using minus, and if the count is less than 0, so we can like maybe we can place the process in the queue and then block this easy process. Okay, if we do have a signal, okay, so we will pass it, okay, at +1, and then checking if it's less than 0, then of course we'll move a process from a queue and then place the process on the ready list. So this one is like you even see the weight and signal, right? We like have a decrease and then increase, but we check the count. Okay, but this count will tell me how many processes reading in this queue. Okay, so of course it's still less than 0. That means there are process waiting in queue we need to execute, and that's why you see the checking condition. Okay, so still like will be less than 0 or equals to 0 right here. Okay, so we'll keep checking. And if we want to implement a binary, so because we talk about a binary semaphore right here, so compared with the integer count, we use the enum. Okay, so we say either 0 and 1, right? So values right here. So when we pass the binary semaphore as and checking, okay, so if it's equals to 0, we flip to 1, then we change it to 0. Okay, and then we will like execute like adding it to the queue. Okay, so if the queue is empty, then we'll put it as a 1. Okay, and then if not empty, then of course we'll remove a process from the queue and then put it to the ready list. So here's the structures. Okay, so you can remember. So what's the differences between the regular semaphore right here? So we have using count. So we have the decrement, okay, and increment, okay, using count purpose. So at least we're adding it. For this time, we will change a little bit. Okay, so it's the same weight, and then this one is like adding a cube checking was a swap it. So if it's for weight, we need to change it to 0. Okay, and then we can compare right here. So when the queue used to hold processes waiting on the semaphore, then a strong semaphore, we try to guarantee so no starvation. Okay, usually this one means they practice enforce that first in first out queuing. Okay, so that means that which process comes in and then there comes out, so they don't have to wait too long. Okay, too much time. Okay, and so we can guarantee all the processes eventually get a chance with a critical section and resources. Okay, so this they can execute. Because when we have multiple different mechanisms, but at least sometimes we'll put a process in the never execution, like starvation, so kind of like waiting, but they never being executed. But for the weak one, so more opposite, so it doesn't let specific orders. They allows for some mechanism like priority based and doesn't necessarily guarantee no starvation. So these are called weak sample. So depends on. So we have a strong and weak one. Okay. And for the mutual expression, when we decide, if you slightly remember, so we can like let's say we have the process define the n and then semaphore using 1 right here. So if we have the process, of course, we will execute a while loop. We're using the wait, okay, right here s, and then we execute the like critical section, and then have a signal, okay, and then maybe have something else. So here is like we can use the semaphore to execute. So we can just adding the function. If you see like when we implement it, then based on different type structures, so we can see of course this time like we can clarify using the same weight or the same way is binary one, so using a B. So this one you will see the example we using the just a regular semaphore using a counting, okay, and then just giving you some like example right here, telling you those like shared data protected by a semaphore. Okay, let's say if we have a queue and then what's the value like in the semaphore log, so it's like 1, okay, and then maybe we have nothing on queue, 0, it's a queue, and then we have a B, okay, and then we'll getting a same weight, okay, then we will minus it and then same weight, okay, minus it and then same weight, okay, so maybe we can execute and then the same signal, so it will getting a log 2 and then we will plus 1, so plus 1, okay, and then it will change to -1, and of course if we add another signal, okay, we'll plus 1 again, okay, if we get another signal then we'll plus 1. So here's a idea, okay, just like using the semaphore, okay, the regular one. So just like be careful, this is like normal execution, so can the process is parallel, but the critical section they serial, so we only can execute those like the critical section, okay, when we like have getting the same weight, okay, when it grabs it, we'll execute that critical section will be right here, okay. Maybe for others it will going to be in block, right? So right here, because even in this time, if you want to get it, but because we already have a critical section, so you cannot do anything, so we have to wait the previous one, okay. So maybe we have signal, then okay, it's done, and the next like process speed can able to get it, okay. So once you release, that it can execute. Once you have a signal, then it release. In this situation, it doesn't um like showing you maybe the time how long this process like taking, but just you need to know of course we have to wait until the same signal like this one, okay, plus 1 execute, then release it, then of course then you can execute another process, okay, and wait until it like completes and release again. Of course we maybe have like A B C D E F G process, okay, reference, okay. And later I will let you have a practical exercise like talk about what's the producer and consumer problem. So you can study about it, okay, and then learn about this one. So it's like there's maybe one or more like producers like generating data, okay. So no matter records or characters, okay, and we are trying to placing in a buffer for processing, okay. Also we have the consumer, maybe one or more customer, so taking items out of buffer and processing at a time, okay. So we need to constrain to prevent overlap of buffer operation, okay. So if only one agent, either producer or consumer, may access the buffer at any time, right? So since they are like both like modifying, either like adding it or removing it, okay. And also another problem. So if the buffer is like finite, okay, how can we prevent the producer like from adding, okay, into a full buffer? And also how can we block the consumer when the buffer is empty? Okay, so this like don't like busy on waiting or check, okay. So here's the things. Then there are two problems where they can adding it or removing it. How can we make sure only one can access it at a time? Also another one, make sure like the checking condition. Okay, we have the limited. Okay, so when it's full, we cannot add anything into the buffer, or when it's empty, we cannot remove it anymore. So we need to think about it. So let's say we putting the always putting a while loop. Okay, if we try to produce it, we try to adding be in, okay, impact plus 1, adding 1 the value, so we adding in, so be 1 2 3 5, okay, so we're adding it. And then for consumer, so it's true, so make sure the in is less than out, okay. So if we're doing this, that means I do nothing, okay. If the in is less than out, okay, then it's coming out, But if we can do that, then we're putting the so the word, like let's say the W right here, so is the B would be the buffer. Okay, so what's the out pointer right here? Okay, and then every time the out will pass one, so you keep adding. Okay, and until like it hits the equal, then we will have like, let's say we have the while. Okay, so if the inside the equals, then of course, or like because we never able to make the like out pass after in, right? So if we more than out is more than in, that means that you're reading more than buffer, right? So that's why we're checking, make sure. Okay, so in have a condition like less than equals to out, then it will stop. Okay, here's the situation. But when it hits equal, then it will stop. So mainly this is a condition checking, and then we consume item W. So right here, so it's a producer. And in the solution, if you look at this part, okay, we have maybe we implement the binary semaphore, if you remember. So if we adding the call the produce, and then we have the same weight B, okay, we pass in semaphore. Okay, so if you know the enum, we just like adding the 0 and 1, just like flattening it. Okay, and then we can append it. Okay, so then we can add the integer number n. Okay, so if we say, okay, n equals to 1, then the same signal B delay, okay, and then there's the same signal S, okay. So it's doing in this one, and the same weight B in consumer, they can like delay waiting it, and then when we execute the while loop, and then we have a same weight B, okay, and then we'll take. So one is append, one's take, and then and minus. Okay, when we take something, of course we'll minus the total, and then the same signal. Okay, and S. Okay, we can execute the consume, and then if n equals 0, and then we will like execute the same like B with delay. And you will see right here, we are going to use the same signal, okay, the binary, and also we have the producer and consumer right here, okay, to reading the buffer. So all these, but what's the problem right here? Just like possible scenario, okay, so because when we have a producer consumer, okay, and for the delay, okay, whatever, it doesn't matter in the beginning like 0, so we're adding 0 plus 1, and then if equals to 1, okay, right here. Okay, same thing delay. Okay, we execute the delay. Okay, true. And then n equals 1. Okay. Because we already plus 1. And then we have the same set of B. Okay, and then we have the delay. And right here, and the n. Okay, so we, and then n minus minus. Okay, and then we will release the same single B. Okay, so we change it. Okay, and when we go back to the same signal B and then plus 1 again, same signal. So right here, you can see just like following, and then we have the wait delay. Okay, so it's 1, and then same weight. Okay, so same weight. So we change the binary same weight, and then -1 0. So right here. So far right here, just like there's a white area, so just like some critical section can be controlled by the semaphore S, right? So right here you can see. So we like before wait, we execute checking. So we can like compare right here. So if the condition. And what's the better way like doing right here? So you can compare. So right here we have some like local variables m is like you adding it, and local variable m will equals to n. Okay, and then checking the n. So right here like to giving like infinite like buffer producer right here using the binary semaphore, mainly checking. You see the differences like originally. Okay, so because we access the n directly. And this time we will assign a local variable. Okay, this local variable, once we have the getting the semaphore way, and then enter the critical section, and then we will make assign it equals to n, and then we can compare it. Okay, so this is a correct solution. And also another way we are doing for the counter countering semaphore, that means the default, the one we are talking using n, okay, equals to 0. And then we can use the sandwich append, okay, and then signal s and then signal n, okay. And then for consumer, also we can like of course we will like for wait for n and then wait for s, and we will take it, able to finish, then we release the signal s, okay, and then consume it, aiming for execute the consumer. Then you need to think about one thing. If let's say the right here, let's say if we block, okay, one, so if let's say the producer if going to want to insert into the full buffer, okay, and then or the consumer want to remove from the empty buffer, okay, so when they like keep moving empty, and if we have the finite circular buffer for this one, then we can change it. So we need to think about how can we unblock it. So let's say if we have the consumer, there's a item insert, so then we can do that. Or the producer here, like we say, we try to remove it, then we can do it. Okay, so it's like if we can remove the empty buffer, so we need to do that. Either way, if we want to block it, and just like give you more source code. So let's say if we have the loop and then every time, so this one is more like it's a circular way, because if you know, okay, so we just like checking. So when we the in buffer +1 and the modules n, like n is like how many, if you learn the circular queue, so it's the exactly same idea. So it's a circular queue just to make sure, okay, so modules by n, okay, if like equals, then we're not doing anything. So that means we hit it is a full, okay. Or the in equals to out also is same, okay. So when they overlap, that means that either it's empty or it's full, okay. So we are not doing anything. For the west, it will be the same. And so far right here will be the semaphore showing you we have the s equals to 1 initial state, okay, n equals to 0, okay, and then we have the size of the buffer, okay, then we can decide here the buffer. And of course both of them, they will start with the while loop, okay, producer and consumer, okay. Let's say we execute the produce first, and then we have the sandwich for the e domain size, okay, and then we have sandwich for the s, okay. Then we start doing append, and then we release S and then release N. Okay, so it's the same signal N. Okay, so right here would be the 2. And for the consumer, it start with the sandwich N and then sandwich S. So here's like in the opposite side, you see right here. And then we need to execute the tick, okay, for the producer and the consumer. One is pen, one is tick, and then we can signal S and then signal E, okay, and then consume. This is one more execute, okay. And you just like remember the kind of the structure, okay. Even if you need to fill out like all these like which part we are how going to put, then you need to know their orders, okay, correctly. So when we implement the semaphores, so we need to like imperative like that, like the sandwich or like same signal operation being like implement as an atomic like primitive. This is more important. So it can be like in hardware level or firmware level, okay. And then the software scheme like the checkers or like the Peterson's algorithm also can be used. We have not yet talked about all this algorithm. Later we have other algorithms we're going to be discussed, okay. So we can use like one of these hardware support scheme fundamental exclusion, kind of like this. And just like showing you the one more semaphore primitive example. So we have a semaphore counting, we have a queue, right? So here's a given in, so there's a thread. So we have a wait function, signal function, okay, showing the minimus and pacify this word learn. So if the count is less than 0, okay, so we will place it into the queue, okay, about this process. Or like if the count is less or equal to 0, then we remove it from the queue and also place it to where delete. So it's a signal. Giving you more like details like how can we using the flag and queue to really implement it. So we have the wait while and then minus if I can. So we need to set the flag to 0, okay, right here. And then the next day for signal. Okay, so we are checking, and when we try to implement, we will doing compare if you still like if you remember the compare and swap. So we like check the flag. Okay, so make sure the flag 0 and 1. So if you remember, we're going to have a test ready one. So make sure it, and then is it return 1? Okay, if yes, okay, do nothing. If no, then we can move on, and then we're checking the flag. So here's a compare and swap function. Okay, it's going to execute. And so far we are going to finish in this part, and we will start our monitor in next time. Okay, just reminding you, we're going to have a short quiz. Okay, just there's some multiple choice. Okay, pretty easy. Okay, you should be able to finish it. Okay, just like calculate for help you to learn regression. Okay, just letting you know. Um, that's it. Thank you.